bridge, right? So then they have concerts on like each corner, and just walk through and have like the beers and stuff.
Cool.
And snacks.
Did you? Yeah. Oh, yeah. Got that, got the hat too, maybe? It's supposed to come with, part of the hat. Only a certain type of hat fits my head. I was gonna say, I got a big head anyway. Yeah, so. Basically only like trucker style hats. Look all right on the end, otherwise they end up getting too shallow, they look like. They've been sitting on. Yeah. I'm in the same boat there.
With that conversation.
Yeah. That's from kind of, you ever been to Oktoberfest?
Yeah, I've been to it. No. I don't drink anymore. I kind of,
Yeah.
a few years ago, I became a Buddhist. They don't drink.
Yeah.
It's like one of the things. So anyway,
That's fair.
yeah. Actually, it's not that big. Like it isn't really that big of a deal, but Oktoberfest, it's not as much fun, you know. It's basically like, you know, drinking parties. So, but, you know.
Yeah.
I never drank. I don't like the taste of it, so I just kind of gave up on it.
Yeah, I don't know. The more you think about it, anyway, I don't. Anyway, that's the thing. It's the more you think about it, it's kind of a stupid thing to do.
Yeah.
I mean, if someone introduced the idea, if it didn't already exist, you know, so it probably wouldn't become popular. I don't think. Well, maybe it does because animals drink, right? Like when fruit gets spoiled. Yeah, it's like monkeys eat fermented and whatever fruit. And they kind of go to it. So who knows? Anyway, I brought these things in. So these, I just saw them on the way in. I thought at some point we could do this. But I'll do it now. So this stuff is, impurities. Well, the same thing as water and this PVME. This guy is working. Yeah, so we have that. This working. Right, so for polymers, you reduce these things by the molecular weights. These numbers will be like 100,000. It's basically if it's in this is a PVMU. So it's that's basically caustic glue, more or less. Like caustic glue is methyl ether, and caustic glue is polyvinyl ethyl ether. That's like another CH3 here, and that's CH2. It's called a vinyl ether, so you can make it with a free radical flame solution. Anyway, so there's H's on the end, so it's a polymer. And then because this is such a big number, like these things go basically to zero. Right. And this, if it's in solution, like this number is almost 1, so that thing's like 0. On of 1, 0. And so there's no driving force from mixing of a polymer and a solvent. Usually won't mix. Same with two polymers. The two polymers both of these things are 100,000, so both are zero. Right, so even at 50-50, two columnar. So you don't have this entropic, that's the delta S of mixing. You don't have that to drive this lower, because these would be smaller than 1. So this guy has to provide a negative energy of mixing somehow. So you have, I mentioned before, so you have like B over KT and then A. So you'd have some format for this like that. Like A12, something like that. So the negative part, as you go to higher temperature, the negative part disappears, and you have only the positive part. So that means that you get it inverts the phase diagram when you plot delta G versus temperature. Instead of being, let's see, how does this look? So this will always be like this format, like you have, this is the two phase that's critical. These are different temperatures. And then this is single phase. And these are the two phases that are in equilibrium because the slope of this thing is mu. So you have like mu A, let's say this is, and then mu B are equal to each other. They're the same slope, so those 2 points are in equilibrium. So anyway, that will give you a phase diagram and temperature, but if you have this kind of, this is called lower critical solution temperature. If you have that, this is actually a high temperature, like T2 is higher than T1 because of the way this works. And so then you'll get a phase diagram if you plot it. Oh, this isn't T, this is X down here, sorry, like X1. So this is mu A1, phase A, phase B1, component 1, if you have X1 down here. So you have temperature versus X1, and it's going to end up with a phase diagram like that. And you have this is called a lower critical solution temperature. This is like a critical point, and this is a lower critical solution composition. The normal case is that this thing's positive, and the negative comes from this entropy of mixing. And then you get the normal behavior like a UCSD. Or you take a solution and you cool it down at phase separates. If you want to wash up something that's spilled, use hot water. That's the idea. With this thing, you use cold water to clean it up. So it's kind of an odd thing. Anyway, this is PBME in water. And it turns out like this critical point, when this is water, is right about at like room temperature. So basically, if you put your hand on it, it'll go into this two-phase region. What happens is you'll get what's called a cloud point. So basically, the thing turns into milk, like it'll look like milk, like almost like a colloidal solution if you hold it in your hand long enough. And then there's kind of different compositions here. So theoretically, if you knew the compositions, you could map out this phase diagram, but it would kind of look like that. Like you could get these different points by seeing what temperature it turns into milk. It turns into looking like milk. So, but in fact, like, what do you need to know? Like, so look at this equation, N, X, and this is actually replaced with volume fraction for the Floyd-Huggins equation to take care of, I guess, the shape of the units are different, like the solvent and the polymer mirror units are of different shape. I think that's why they do it. It isn't well explained anywhere, like what's the advantage of volume fraction? But I think when they explain it, they say it's due to the shape difference. The shape of the two things mixing aren't the same, so the number doesn't matter as much as the shape. So you put the volume in. Anyway, so you can convert from mole fraction to volume fraction to the density. So what the density of a monomer is, it almost adds another fudge factor into it. I'm saying, like if you don't, like, say you have a chain of carbons, and what's the volume of one unit? Like that gives you the ability to make something up in a sense, right? So in that way, using the volume fraction is almost like a fudge factor. So anyway, but the whole equation has just one parameter, just this A12, or two parameters like A and B if you break it into two like that. Right. So really, if you just have A12 in a normal solution, you just need one cloud point, and you can predict the whole phase behavior. You just need one composition, one cloud point, and you can calculate the whole thing. If you have A and B, then you need two cloud points. But with two cloud points, then you can predict every other phase point on this curve with that equation, right? As long as this equation again is going to be symmetric. So if it's asymmetric, then you'd need three cloud points because you need one more term. It would be a two-parameter Margulis instead of single. Right? And Floyd-Huggins at A is called chi. So it looks a lot like the X's that I put here. But basically it's called chi instead of A. Chi 1, 2. It's of the same form. So chi 1, 2 would be this thing. So I mean the form's going to be, it's going to be an average delta energy. It's going to be the coordination number if you're using a lattice, and then it's divided by KT because you should have flattened by KT here. I think that's it. I might be missing. Oh, there's a volume in this, like the volume of the kind of the lattice point, E star. And then E, delta E is going to be the interaction energies of 1, 2s minus interactions of 1, 1 plus 2, 2 divided by 2. Let's see. That's it. That's what delta is. So it's just the average interaction for a site, energy for a site in terms of 1, 2 versus 1, 1, 2, 2. In other words, a 1, 2 has to replace half of a 1, 1 and half of a 2, 2. So this is the delta E average. It's like the average that one of those interactions would do. Anyway, so I probably pass these around. You can just hold it in your hand, and you'll see that it will turn cloudy depending on your body temperature. Some of them measure the. Take your place and just take one, yes. And two. Oh, you haven't answered. All right, actually, we're right. We'll get it. We'll pass you around after. See if you guys can change the temperature. Hold it as tight as you can. Yeah, if you're a cold person, then it won't cloud. If you're a warm person, it will cloud. So it's kind of a sideshow thing in a sense, you know. You can test true love with it too, or whatever. But anyway, so yes, that's kind of the story. You'll see that a lot in polymers. Like there's so this is used a lot because the polymers like this. So there's also penny PAM, which has the same behavior. I'm just not sure I can draw it. Let's see. Penny PAM is poly in isopropyl, like penny acrylamide, amide. PNIPAAM, penny PAM, right? So it's also a vinyl polymer, which is easy. So it's got carbon, and then it's got an N-isopropyl. So it's a propyl, isopropyls like that. Acrylamide. So it's got that, and it's got a NH. Yeah. Oh, sorry. Yeah. Why don't I just actually I can just Google penny PAM. I don't have to draw it. Not the easiest thing. Something like that. That's it. Yeah, so it's this thing. So you have there's isopropyl, so 3 carbons, and iso means it's the same, so it's symmetric about that. It's got an amine and a hydroxyl here. So it's a mimic for proteins have the same structure. In other words, proteins have a hydroxyl and have an amine. So this amine can hydrogen bond with that hydroxyl. So this molecule can act like a protein, but it's a synthetic vinyl polymer, and it's free radical polymerization. So just pour the monomer into a pot, and just boom, you make it, no problem. Put in a free radical initiator. So it's easy to make. And it has exactly the same, this PVME has the same kind of behavior. So the phase separates around body temperature. So this penny PM's used for biomedical stuff a lot, like drug delivery. So if you make a gel out of this and swell it with a drug, and then when it gets into your body in a hot spot like a cancer area, it squeezes the stuff out. And people also make like plumber chains, and they stick these penny PMs off the side, and it makes it kind of dance. It makes it change shape when it gets to different temperature parts of your body, because it phase separates with the temperature and it heats up. So there's quite a bit. I think there's a lot about penny PM. There's not so much about PVME. I'm not sure why. I think because this thing's looks like a protein. So it can both of them have hydrogen bonding, and that's why they have specific interaction with water. Right. But the weird thing is PVME also has specific interactions with polystyrene. So it mixes with polystyrene because the aromatic group and this polar group somehow interact with each other. So it has the same kind of LCSD behavior with polystyrene. So you can mix it in with polystyrene and make like a blend with it. So it's kind of, penny PM doesn't mix with anything, just water, so anyway, but you can graft it onto other things like PMMA, things like that. So anyway, so this is like a popular item and to do biomedical stuff, and it's got this phase behavior. Is that business? So let's see, I just wanted to finish through this and go through the homework stuff. So diagrams, this thing. So just make sure I covered. I think I went through most of the stuff in this section, but not sure. Went through so in other words, Fleury-Huggins uses this volume fractions. That's how it relates to mass fraction. The mass fraction relates to mole fraction. So if you know the mole fraction, the number of moles times the molecular weight gives you the mass, and then the mass times the density divided by the density will give you the volume. So you'd have like XA times divided by XA times molecular weight divided by density, and then divided by that same thing for A and sum to B to get the volume fraction from the mole fraction. Right, but they're just related to each other by numbers that you should theoretically know, like the density and the molecular weight. So whenever you need to convert, it's important to be able to convert these things, because if you make the stuff, you're going to use mass. Usually you're going to weigh it out, unless you're doing liquids, and it would be volume. So you have to be able to convert back and forth. And if you're doing like a chemical reaction, you need to know the moles. And then Fleury-Huggins uses volume, and then most solution theories use moles. So if you're weighing in mass, you have to convert to moles. That's kind of your most common situation. So mass by molecular weight, and then just sum up all the other components to get the mole fraction. Right. So then we went through this in the last quiz. Oh yeah. All right. So there's one other thing. So people said, I forgot. And when I looked back at the notes on the other quiz, they said like, oh, this magnetic transition is reversible. Right. So you have to be careful what you say. Like, all right, so reversible means delta S equals 0. That's what it means. Because delta S is going to be like Q by T. Right. So it means when you have delta S, it means you're converting to heat, and heat isn't reversible. Heat disappears. Same with cooling disappears. So cooling or heating disappears. It's not reversible. Right. Some things are reversible, like laminar flow. Cooling and heating are not reversible. That's the end of the game, right? So you're going to have a gradient in temperature. That's kind of the cooling and heating. So saying something's reversible when the whole process is driven by delta S means you don't have any idea what's going on. That's just like saying, put a sign on your forehead that says "kick me" or whatever. So you should think like I know why you said that, because here's this block of metal, it's sitting there, you turn the magnetic field on, you turn it off, and it's a refrigerator. So it looks like that's reversible, but it isn't. It's not reversible, because delta S is the thing that drives it. Anyway, that was the only thing that I forgot about the last homework. So then, so we went through this business of the three ways to get this ideal mixing equation, this thing with the x ln x thing. And then talked about entropy. That's an ideal solution. Ideal solution has no volume change, no enthalpy change, because it's just entropic. And delta G is just delta S. Right. So then that's the Hildebrandt model, which is the basis. It's the basis of the Flory-Huggins. It's almost the same thing, except you swap out volume fraction. And then we said, like, there's two ways to get this real solution. So you can use a Hildebrandt parameter, make binary interaction parameter. So the probability of 1, probability of 2, and then the energy of a 1-2 interaction, that's the enthalpy, excess enthalpy. So that would be, and you can also say swap out X for activity and just use the same as the ideal solution, but use activity instead of mole fraction. And that brings up this idea of activity coefficient, which is a modifier for the composition. And if you do that, you realize log of this times that is log of that, plus log of that. So you end up with that the excess looks a lot like the ideal equation. The excess free energy of mixing looks like the ideal, but you swap out the mole fractions and the log with this activity coefficient. So activity coefficient is one way to talk about non-ideality of mixing. So that becomes like the main theme of a lot of papers. People are just talking about activity coefficient. Like if you go back up here, so you have like activity coefficient of bismuth lead, heat transfer fluid. Let's see. So all they're doing is calculating activity coefficients. Right. So saying like the excess Gibbs free energy is this like this volume thing, whatever, however they did it, these two things are going to be the log of the activity coefficients. Log of that thing's log of the activity coefficient. Right. And then he figures out some kind of interaction parameter for this. Like a Hildebrandt interaction parameter just adds more terms to it. So you can see any thermo paper you pick up on mixing, it's going to be like the same within this same framework. Like you're looking for the things that you can understand. Maybe you don't understand them right now, but basically there's certain themes that are going to repeat, right? The activity coefficient, then this Hildebrandt kind of parameter. Once you realize where those terms are, then you can start picking apart like what it is that they're doing, like exactly what they're doing. So you need to kind of know the general framework and then figure out how that like fits together, you know. That's the idea of this. So anyway, so I don't know. Anyway, they end up with like plots of the free energy. There's just a few example papers. These are all like recent, pretty recent. I think I didn't add any this year, but it's 2020. These are all kind of recent papers. Activity coefficients for electrolytes. Then you add in like the term. So I wanted to, at the end of the next section, I wanted to throw something in about kind of batteries, you know, thermodynamics of batteries. I think we can squeeze it in if I talk fast enough. But anyway, electrolytes, stuff that there's a lot of research going on in that now. So I think that this should probably be included in this class, you know, a little bit about it, just enough so you know what the Nernst equation is and things like that, that things that people are using for batteries. Anyway, so there's this thing uses like the Debye screening. It's pretty involved, this paper, but basically in the end, they're going to end up with the same kind of equations. We'll talk more about this at the end. Like they end up with the activity coefficient down here in terms of like a Debye screening length, some other things that we don't know about yet. But so some of these are pretty straightforward. Some are like anything that's going to have to do with polymers. So they're mixing, I think this is like asphaltene and petroleum fluids. All right, so this is an equation of state, this NRTL-SAC. It's like the Prias thing, Peng-Robeson equation, but it's a little bit more involved. It involves like volume of mixing differences and things. Like it's something petroleum engineers use, you know. So, but you can see like, all right, so this paper, it's kind of, anyway, like we saw before, like the free energy change is going to be RT times ln of the equilibrium constant for a chemical reaction. And the equilibrium constant It's gonna be like the product mole fractions divided by the reactant mole fractions in a chemical reaction. So he's taken like, and if you take the ratio, it's gonna be the one minus the other would give you the ratio of the two. So these are the mole fractions of of the liquid and the vapor or something. And then he can get the equilibrium constant from that and uses that to get the free energy. It's kind of interesting what they do in this paper. It's asphaltene's this stuff. It's like graphene kind of, but it's low molecular weight. And it kind of clogs pipes in the petroleum when they get oil. So asphaltene, it's what they make. Asphalt is made from asphaltene, more or less, so it's kind of a problem that you have when you pump oil from crude oil from the ground. This asphaltene precipitates out. So people want to know the phase behavior. At what temperature is asphaltene going to come out of the crude oil and clog the pipe and then make the whole operation stop, or the thing blow up, or cause the whatever happened in the Gulf of Mexico. Right, so things like that. So they want to kind of know that. So they're trying to get activity coefficients for this tar-like stuff, these kind of things. So there isn't one structure for it. So they just show like a generic structure, and they can use that for computer simulations to figure out when the oil well is going to blow up and the Gulf of Mexico is going to die, whatever. So it's kind of like thermo of the whatever. Let's see, carbon nanotubes and polymers. So this is more like going to use Flory-Huggins as a polymer mixed with something else. So, and they're using the del parameter, the square root of the cohesive energy density thing, and then calculate how the things mix. I think this is in the notes, right? To how you mix graphene in with polymers. Drugs and polymers is kind of the same story, and that's some other thing. So anyways, there's a bunch of things that are kind of going along those lines. Let's see if I can get back in time here. Let's see. This is PowerPoint. You should have like project here somewhere right here. All right, so yeah, so you get this idea, like you have this equation, the ideal part, so you just want this excess part. So then you're going to write the excess, and the excess, so the excess Gibbs is going to be this Hildebrandt kind of term, or it's going to be like the activity coefficient term, right? Because this is that times that. So if you take out the ideal, you just have ln of gamma, right? So it's going to be either of those two formats to get the excess free energy. So yeah, the excess, let's see, where's the list of excesses here? Not here. Yeah, here's a list of excesses. Excess, so there's some number that would be the excess. So this would be what you call non-combinatorial entropy. So this is combinatorial entropy, like you throw the red and blue marbles in the thing, you shake it up, it mixes, right? And then that's going to lower the free energy. But you can have another entropy that happens, it's non-combinatorial, it doesn't involve shaking the marbles, in other words. So that might be something like the hydrophobic effect. Like you have an oil droplet, the water organizes around the surface of it, right? So that's going to decrease the entropy, right? So you're going to lower the entropy because of organization of the fluid. So this is why you get, instead of the Hildebrandt enthalpy term having just a 1/T dependence. In other words, you have free energy over temperature. So Hildebrandt has some number over temperature, then has another number that's not temperature dependent, which is the entropy, right? So basically, if your solution, if you're using this term, then this non-combinatorial entropy term gets buried in this enthalpy, excess enthalpy of mixing. Then you have the A minus B/T for the Hildebrandt. Right, so that non-combinatorial entropy accounts for basically organization that happens when you mix things. Could be other stuff too, like things, say the structure, when you mix the two, the one thing folds, so it might be, then that's kind of almost crystallization happening. So it's the organizational change of that matters. It's not random, so it doesn't have a lot of configurations, goes down to one configuration when it crystallizes. then there's a big change in entropy, like there's a loss in entropy, which means the free energy goes up, right? Generally, this thing's going to make the free energy go up. That term's going to make the free energy go down. So that term, that delta S excess entropy ends up being buried in the enthalpy usually. Then any change in volume of mixing is an excess because the ideal has no volume change, right? So you can have excess of any of these terms, and you'll see papers where they talk about the excess depending on what they're interested in. So you might have like volume change might be the most interesting thing, and so it might just be a paper about like here's this paper, it's from the book, but basically it's about volume change on mixing of different alloys, right? Lead 10 and lead SB, which I don't know what SB is. One has an excess, so positive deviation from ideality. Ideal would be a straight line at 0, and then a negative deviation from ideality, right? Negative because the things like each other, so when you mix them together, they take up less space as they're kind of clustered in. And then positive is because they kind of don't like each other, but they still can mix. So it expands the volume and they mix, more or less, right? So somehow you'd have to mathematically say what I just said, to kind of explain this. So papers like this paper would describe mathematically how to do that. Generally with some fudge factor, just something that's going to account for the volume change. And in that case, you couldn't use mole fraction in your mixing term because you need to have a volume fraction that would account for this change in volume, right? So that's a reason why you need a volume fraction, is to account for this kind of change in volume in your mix. Anyway, then that's okay. This is some iron nickel thing that's in the book. I talked a little bit about the Henry's laws, this infinite dilution, and then when you get to the pure components, the activity always goes to 1 because the activity coefficient always goes to 1, and then the activity is going to go to the mole fraction. So the mole fraction, when you get to pure iron, and this is amount of nickel here, the activity which is plotted here matches the mole fraction. So it's a straight line of slope 1. That means the intercept here is going to be, or the slope of that, the intercept is going to be 1 for the ideal, or be 0 for the ideal. The slope is 1. So the activity coefficient is 1. And then for this one, the infinite dilution one is not 1. So that's the Henry's law, is this infinite dilution, the intercept of the activity here, and the Raoult's law is that thing. So it's like you can have Raoultian kind of condition or a Henryan condition as kind of your basis for calculating like the chemical potential of a component in a mixture, right? So that you'll see, like you can see in those papers, like they're calculating this infinite dilution activity coefficient so they can predict what the chemical potential is going to be and get a equation of state from that. In other words, get from these two numbers, they can get the enthalpy of mixing under a Henryan model. So they can get the A12 using those two numbers, using the thing that ln of gamma 1 equals x2 ln x2 times A12. That equation that we had before, like once you know the gamma under some condition, then if you want to know the A12, it's going to be like x2 A12 is ln of gamma 1. And ln of gamma 2 gives you x1 squared A12. So you can get the A12 from either of these guys. And then from the A12, you can get delta G, and from delta G, you can get those curves, and you can predict the phase behavior. Or you can get the cloud point from that, or whatever phase behavior you're talking about. So this kind of curve, this is a phase diagram, like temperature composition. That's for a liquid solution. Like liquid, oops, sorry. No, it's doing that. Liquid, that's for a liquid. So there's different things. You can have solid, liquid, solid, solid. So you can have two crystal forms that are mixing, or you can have things mixing in a solid solution, like an alloy. So copper and copper and zinc mixing together, right? In a single crystal, in a solid solution crystal that's in equilibrium with a liquid of this similar composition, right? So basically you can have different kinds of things, but this phase diagram is like that. I wrote it like an LCSD, but that's going to be a liquid phase diagram. There's two phase here, it's one phase here. And that's based on this kind of the delta G versus composition. It's like that, and you have the 2 points that are going to lead to 2 points here. This is an isotherm. It's at one temperature. Right, so you can see, so you're looking for, so if this thing is like that, then that goes back, that's single phase. If it's like that, then it's two phase, because at any point on this, if you do a fluctuation up and down of equal amount, the up is steeper than the down. That means the delta G increases. Whereas for this thing, if you do any fluctuation, right, then the down is steeper than the up. That means that the delta G drops. That means the fluctuation continues. So it'll just continue to fluctuate more and more until it reaches. So this is the frown face, and it's going to reach this happy point where the smiley face is. Right, so it's frowning here, and it's going to go to this happy thing here. So the problem, so that works in the middle, right? But there's an inflection point here where that doesn't exactly work anymore. Right, so if you're in this region between those two, which on the phase diagram kind of looks like this line, then you have a problem, right? You can't, in other words, it's not a frown face. So you're not going to, it's the composition you put in here is kind of happy there, but it isn't really happy. So it's metastable. It's not in a stable region. It's not at the equilibrium points where it would be happy, but basically it doesn't change because it's in a metastable state. So if you're in that region, the only way for you to get to these places where you want to go is if you have a seed. So if you throw in seeds, then it can nucleate at the surface, and it can grow, the phase can grow. So the only place where you get spontaneous phase separation is in the middle, of that phase diagram, like in this region. It's a temperature composition. So that's called the spinodal region, and these regions are called the binodal for liquid phase separation. And what you see from that, the binodal ends up being that you'll grow from seeds. So you have this kind of race of growing from dust particles, and it'll grow like that. Spinodal, on the other hand, if you're in the middle of that, spontaneously decomposes. So you end up with a thing initially that looks like a spider web. Like if you could think about what composition fluctuations would look like, and they look a lot like the temperature distribution. So it's hot and cold here and there. It's going to look just like that. And if you try to draw a picture of that, it would end up being like a 3D spider web. Right? And that's what spinodal is, just going to, every composition fluctuation that exists due to thermal fluctuations and atomic motion is going to just grow. Right? So it'll just decorate the existing kind of random web-like structure. Right? So the spacing of those things, though, of those webs, depends on the diffusion coefficient of the atoms that are separating, or molecules that are separating. Right? And it's going to depend on this, like A12, the potential, or Chi12. So what's the potential that's driving that atom to go over into the two phase? And it's going to depend on the temperature, like right? So even though the thing looks like a random mess, right? Everything within that random mess is spaced at a fixed size, like a size that's quantized almost, depending, and you can calculate what that size is based on the transport properties, fusion coefficient, and the thermodynamics. So it's a balance between how fast can I get there and how much do I want to get there, right? And the balance between those two decides how far apart these things are. So even though the thing looks like a random setup, if you shoot a beam of light or X-rays through it, right, and it's of the right wavelength that matches that size roughly, then what you'll see is a ring. You'll see like a diffraction ring from it. Even though, so you have a completely random system, you shoot a beam of light through it, you get a ring, which usually means perfect order. Right, but it's not spots, it's a ring because they go in any direction. Right, so basically from the size of that ring, you can tell the spacing, the average spacing of those domains in a spinodal. And you think that that could be used to make something nice, like a good sponge or something, or some kind of a sound absorbing material, things like that. But it never has actually been used for anything. Because there's a problem with this whole scenario. The problem with it is you draw that phase diagrams. This is UCSD, temperature, composition, and then this would be the spinodal. This is spinodal. This is nucleation and growth. So say you make your material, it's in a melt. That's liquid, one phase. This is two phase. So you have to cool it, right? So you're gonna take that and you're gonna like cool down, and you're gonna go here, and you're hoping that you're gonna get this thing that might be a good sound absorbing material, for instance. It's got a lot of interfaces. So, but to get there, you have to drive through this region, and everything has dirt in it. So basically, as you're tooling along, you go through this region, and then it just sucks everything up into this nucleation and growth thing. So you never can get to that unless you can do such a rapid quench down into that, or if you operate right at the critical. The problem with the critical is there's something called critical slowing down, because when you look at delta G versus composition, see it's flat, totally flat, right? So that means if you're here and you do a fluctuation, well, yeah, any fluctuation of any size will exist at the critical point, but there's nothing driving it. There's no reduction in the free energy. The free energy just stays the same. So it's not nothing. So that's called critical slowing down. There's no driving force for anything to happen because everything's happy. Whatever happens to randomly happen, it just stays that way when you're at the critical point. And so you take this route, you have critical slowing down there. That doesn't help. So it's hard to get a perfect spinodal, especially in metal systems. Right, metals are hard to work with in polymers because the time constant on metals is fast. The time constant on polymers is like seconds, and here it's milliseconds or something. So basically, the rates that things happen for atoms is much faster than things that happen for micron size, like molecules. You know. So anyway, most of the studies have actually seen spinodal or in polymers. All the theory of it was developed by metallurgists. So it's kind of an interesting hybrid area. So that's that business. That's the same gamma business. And what else is in here? This stuff, I think I kind of went, this is kind of showing the same thing, but you can't really see the two minima in it. So it's not as useful. It's better to highlight that. So the paper this week deals with this del function, the solubility parameter, right? So Hildebrandt invented this number. He said that this enthalpic interaction would have to do with something called the cohesive energy density. So the energy that's holding the material together, like say you have zinc or something, and molten zinc, something is keeping the zinc atoms to, right? So that's the energy, cohesive energy of zinc liquid, right? If you take the density of that per volume, take the square root of it, that gives you this cohesive energy density. So that's the idea. So you take zinc and copper, you figure out what the cohesive energy, the energy that holds it together is. You take the difference between the two. So if two things have the same cohesive energy, then they mix. Then this enthalpic mixing term is zero, then the entropy just drives mixing, right? So you want this thing to be zero because this thing, it disfavors mixing because it's squared, that's always positive. So this thing always is going to increase your free energy of mixing, so make things worse, right? So anyway, this del becomes like a topic that people chase after because it's easy. Then you can calculate chi without a computer program. Otherwise, you could calculate what the A12 or chi is doing molecular dynamics simulations and seeing how the things kind of interact with each other. So it's possible to get it from a computer simulation. With this thing, you just need to somehow energy then you can just plop in these numbers. So the people have figured out, Hansen figured out this, you could break this down into parts, the cohesive energy into parts. This is a dispersive, a polar. So you can kind of predict these numbers easier from molecular structure, especially organic molecules. And then you can calculate those and then get this kind of mixing parameter from that kind of scheme of things. So the game becomes like, so you can get the chi, so you can get the delta H, you can get the free energy of mixing, so you can predict the phase behavior. The cloud point. Get that thing to phase. His gave up on it. You did? Oh, the window cell work? Oh, you have to hold it, I think. You really have to hold it tight in your hand. But anyway. Yeah, I think the more concentrated one is easier. Maybe. Anyway. All right. So all right, does that business. Oh, and then last time I also mentioned that, like, so all these Hildebrand things are for symmetric phase diagram about 50%. So that generally it's not going to be symmetric, it's going to be skewed. Right. So to get it to skew, you go to like a 2-parameter model that has, so you have a dependence on A and B, that ends up giving you a skewed diagram. And then you can go along those lines and say, like, why stop with 2? Why not have as many as I want, or as many as I feel like I need? So you can just extend that. This ends up being a power series if you figure it out. It's like x squared, xa squared, xa. Anyway, it ends up being a power series, and read the Keefer, figured out what that power series was. It was possible to get this in terms of any number of terms that you want. So these are just allowing for different degrees of skewedness. 2 parameters is enough to predict for liquid-liquid phase separation. Anyway, so what you'll see is that this is, even though this has nothing to do with like a metal eutectic phase diagram, basically all the models are going to be based on this liquid-liquid. It's just like the van der Waals is where you start. You start with ideal gas, and you go to van der Waals, then you go to everything of higher complexity. So here also, like this liquid-liquid thing is the simplest thing you could think of. So then to go to more complex mixing situations, you just take that and kind of try to force, the square peg into the round hole type thing. So this is a model that everything is based on. So I went through how to get this equation, right? How to get this ln gamma versus x squared thing. In other words, how you can relate the Hildebrand or the Margulis or the chi back to the gammas. So the gammas are directly related to those through this is if it's a symmetric phase diagram. Always that. If it's asymmetric, and you got the second term, then there's a little bit more complicated equation that's here somewhere. Here, A12 related to gamma. So it's the same kind of look, like ln gamma is x squared, but then it's got an x1 in it also. Right. So this is if you have a 2-parameter Margulis model. Hey, it's possible to calculate these things. The same route, following that same route that I showed you, where you talk about the molar and the actual free energy change, wherever that is. So here, this thing. You have to just write the equation out. You have the molar free energy, and this is the actual free energy, which is the molar times n. Then you do the derivative of that to get ln gamma. And then basically, if you write it out, you find out that ln of gamma is like this stuff. And that ends up being that equation. So anyway, so you can go through that if you want. Otherwise, you can just remember that it's gamma, ln gamma 1 is x2 a12. Or if you don't need it, you can just forget about it too. The other thing is this Gibbs-Duhem thing. So if you have one of the 2 gammas, so you have that plot, whatever the plot is, to get gamma infinity, right? So whatever that was here. So you can get gamma infinity of one, and you have gamma infinity of the other. don't those two have something to do with each other? Because you're making silicon and germanium into diamond cubic crystal. So you're making a solid solution, so they can substitute for each other. They're about the same size. I think it's if they're within like 10% of the size of the other atom, they'll fit into the same crystal structure. So anyway, these both have diamond cubic structures, so they can mix in the same crystal, right? So you can get an alloy of those two in the same crystal. So you can figure out this gamma infinity for the two, but how do you, if you have one of them, it must be related to the other one. That's the issue. Like one's related to the other. So this is one case where this weird Gibbs-Duhem thing that seems to not be of any value has some value, right? So you have Gibbs-Duhem said that at constant P and T, number times the derivative of the so normally you'd have the chemical potential times the derivative of the moles. In the Gibbs-Duhem, you have the number of moles and the derivative of the chemical potential, and the sum of the two in a binary mixture is 0, right? And then the chemical potential is log of the activity. Well, activity is mole fraction times gamma, so you can break that into ln of that plus ln of that. You have all these things, but if you look at just the mole fraction ln of XA thing, ln of XA is dXA, d ln of XA is dXA over XA. XA's canceled, and you just have dXA plus dXB. If you increase the XA, you have to decrease the XB. So that means the sum of those has to be 0. That means in this equation, all the ones that are XA ln XA, they cancel each other. And you just have the gammas are related to each other. So you can calculate gamma A from gamma B. They're in derivatives, so you have to integrate. But basically, you can get gamma A from gamma B through an integral if you want to. So there's some papers where they do this. You might see this. They say, we're using the Gibbs-Duhem.
My ex used to use a specific shampoo, and over time I noticed that every time I smell this shampoo on other people, I automatically think of her, and this got me planning. For my current girlfriend, every time we got down to business.
Oh, I know. I have the web open, right? Was that me or somebody Oh, on Zoom? Oh, okay. It's Kristen. Kristen, are you listening to a book on tape? You don't have to answer. My wife's listening to like a book on tape. It's like I'm walking downstairs, like, oh, and then she pulled the gun out, and it's like whatever. Or she's walking down the street listening to this thing. It's like, you don't think that's weird? And I bought her some headphones so she wouldn't have to go through this humiliation. She's like, oh, I don't need headphones. It's like, so who knows? Kristen needs headphones. It's like, anyway, this just shows like how you do that integral, So, and then you can relate the two gammas through the Gibbs-Duhem. So an equation that you thought was totally useless kind of might have some use someday, I mean, it looks like a really weird thing. Like, how would you ever use this? The reason he points it out is because, this is one use of it. I mean, if you happen to have one gamma and didn't have the other one. But the thing is, like, if you had one gamma, like you see that if you had one gamma, you have the other gamma. And you already did the composition measurement, right? So yeah, you could cut the number of measurements in half. I guess you only have to do half of this phase diagram to get but basically if you got one, why not just do the rest of the measurements and get the other one? Right. So, but anyway, it could be a back check to see, like, did you mess up the measurement? Then you have to be related in that way. So anyway, so that's that business. So let me just get to the, any questions on this? Kind of zip through it, but hopefully that's all right. I mean, so let's see, let me get to the, this thing over here, wherever it is. Right, the homework is homework 4, right? So we got the homework, got this paper. Is it right? So I kind of went through a little bit of this. One of the things, like someone asked about this, the orientation functions, last question. So this has nothing to do really with thermal, except that if you wondered when you did the magnetic, the ferroparamagnetic, how do you get the orientation order parameter other than you can measure the magnetization of the sample, but if you just have arrows pointing, like there's an order parameter to talk about arrows pointing. This is what that is. This is an order parameter for arrows pointing. So it's this cosine squared Anyway, so that's a cosine between the two arrows, like the tilt angle of the two. So basically the cosine would go, it's 1 at 0. And then so cosine's like it's 1 at 0, then you get to goes to it's gonna go back to 1, right? So that's like 2 pi. Let's see, did I do this wrong? Is that pi or 2 pi? Pi is here. Anyway, if you do cosine squared, everything comes up. So it goes like that. And it's going to get a little bit different shape. Right. So if you have random orientation, then this is negative, that's plus. So the two cancel. So for random, the cosine squared is 0. No. For random, no, this is all positive. So if you integrate this whole thing, it doesn't equal 1 equals 1/3. So cos squared for random is 1/3. And then if you know exactly the angle, this value is 1. And if you're at 90 degrees from it, I guess you're at 0. Right. So you have two other answers. Cos squared theta is 1 or 0. Right. So there's 3 choices here. Right. So random's going to be random's 1/3, then this is 1 minus 1, you get 0. And then if you get the 1, so it's perfect oriented, it's 3 minus 1 is 2, is divided 2 is 1. So it goes from 1 to 0. But if you get the opposite direction orientation, you get 0, so you get minus 1/2 out of this. So that's kind of how this thing works. You have to know which way you're pointing, otherwise it doesn't really work. Right? Like if you want to use as a weighting factor, an order parameter, you have to know which direction things have to point. In other words, if you have an antiferromagnetic where they're pointing in opposite directions, you probably want to use the angle, set that at 0 angle, like when they're opposite each other, so that you get 1 for this when they're opposite. So anyway, I put that in because you'll see that equation or let's see, these are called, I think this is the first order Legendre polynomial, believe it or not. I got it right. Polynomials. So I think that's the first order P blah 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 da da da. At some point it's going to say like cosine whatever. Here, there's a cosine. So somewhere in here it'll say that's the first order Legendre polynomial or something. And then there's also second order, third order. So if you want to talk about orders of, anyway, it's the same thing as the Legendre transformation that we used before, but this is not the same thing as that. It's the same guy. He did 2 things, as far as I know: the Legendre polynomial and the Legendre transform. I probably pronounced his name wrong. He probably did more than 2 things. Basically those are the 2 that I know. So that anyway, this order thing ends up being that polynomial somehow. And this is the first order of that. So you can find this. If people are really looking at this seriously, they do the first and second and third order of this, and they get different numbers for it. I'm not sure the details on it, but basically the first order is the only one that I've ever used. But it's pretty popular for things that, and if you run into a situation where you have things you want to know, like, are they aligned or not, and you have a computer program or some way to measure the orientation, like you could have an IR peak that gets shifted when the 2 molecules are close to each other, and it gets shifted in a different way, or NMR band or something that shows up. They can quantify like how many are close and how many are far. And then you can feed that in to figure out the cosine of the angle, and then figure out what the order parameter is for that, like how ordered are they. This turns out to be like a pretty useful function. That's why I mentioned it. It's used over and over again. Like you see this, it'll come up and you'll be like, what the heck is that? So this shouldn't be something that's foreign to you, I think. Anyway, so he's got what does he have going on here? So he's doing a computer simulation of this mixture of these two quote unquote polymers, but they only have like 4 units in them. Right, so they aren't really polymers, they're oligomers. He's using this is the Flory-Huggins equation with volume fractions, but in the real Flory-Huggins, like that term is supposed to be x1, so I'm not sure why that's volume fraction here. I guess it's volume fraction times volume gives you the component volume. Maybe this somehow works out to x1 when you put the terms in, but generally those are x's and the inside here is a volume. So for whatever reason, he has it that way. And the reference, so this is just the Flory-Huggins equation. I think we kind of mentioned it. The chi parameter is the same as the A12. And then he does computer simulations. I think it's molecular dynamics of these things. And he ends up qualitatively saying that he can see phase separation. Like, so he says that's phase separated, that isn't. But you'll run this thing many times, and sometimes won't be as clear as this. So he's picked out the clear cases where he says that's phase separation. That's kind of a weird thing. Let's see, what else is going on here? Then I think he's calculating the, let's see. Oh, he's calculating the correlation function. Okay, so he uses this Kirkwood-Burr equation, which is this thing. And this thing he calls the Kirkwood-Burr integral, this Gij, which is like the free energy of mixing. Okay, so I guess you need to know the correlation function, this thing, is, well, let's see. So you have some kind of mixture of things, or just say you have some things, right, some circles. And then you're going to say, well, I can find the position of that circle, and I want to know what's the position, like if I go out a distance r, like what's the probability at r of finding like another circle from a circle that I have, right? So, and then so you're going to do that as a function of r, so you'll get a curve like, so if you're at your own thing, it's 1, like 100% you're on your thing, and it's going to go to nothing. Then after a while, maybe you have like a hump, and maybe there might be multiple humps, you know, what kind of thing there is, right? So, and then, so you take that function for one thing, and you're going to like sum over all the possible things. Like you have to go integrate over every possible thing. So it ends up being a kind of an integral around that circle, or be a sphere, and then integrate for every one of the things in the system. So count it kind of twice, like that thing would hit this thing, then you go from this one and hit that thing, right? So anyway, so that's the correlation function, is a sum from one of them out, and then sum over all the possible ones. So it's like a double sum over each one over distance, and then sum over all the possible ones that you could find in the system. You'll end up with something like this, like some kind of curve like that. It's going to be 1 at 0. It's going to be 0 at some point, and it's got kind of a decay to it usually. So, and then if it would have kind of a region like the most probable to find the thing, find the material in it, right? So anyway, the Kirkwood says that that's going to be like have something to do with this free energy of the system. So you can integrate. So you subtract off 1 from that. Because in the end, this probability when you get out to here is the density of the system, right? In other words, if I go out some distance, say what's the probability of finding another one of these circles? That's the density of circles, right? If you go, if this is infinity away, that's the density of circles, and this is like this p of r divided by the density, so that goes to 1. It doesn't go to 0, it goes to 1 when it goes to infinity. So you subtract off that 1 to get this thing on a scale where it goes to 0. Right? In other words, so it has to be 1 when it gets to infinity because of the definition of the thing. So Anyway, so you have to subtract off one to get something that's of meaning here. So you do, so he's got the G of R, this correlation function. So you can see, like, you could easily get that if you do a computer simulation. So like the dynamics, let the things move around and just they have some potential of interaction. So that kind of decides the free energy of the system. They try to minimize the free energy by moving around. Then basically you reach some equilibrium state. Then you can take a picture like this and you can calculate all the spots of your stuff and then figure out the distance of the same stuff. So you could have a correlation function for the PEO and a correlation function for the polyethylene. Or you can have a polyethylene PEO correlation. So it could be 1, 1, 2, 2, or 1, 2. So you can have 3 different correlation functions for this thing. All right, so he's got IJ. So he's got an integral. So G, this Kirkwood Burr integral. Kirkwood, it's kind of interesting. Kirkwood was a guy at Yale, you know. And he let's see if they show this. Oh, not gravel. There's actually a company, Kirkwood Gravel. I think it's like this thing. No, that's not working. There's a picture of it somewhere here. Take, oh yeah, so here, this picture. So you got Onsager, who won the Nobel Prize, right? So it says like they're buried next to each other. They were colleagues in the chemistry department. So it says like Onsager, he won a lot of things. It says Nobel Prize. That's it, you know. And then Kirkwood. So Kirkwood died first, I think, right? Yeah, it's a 76 for Onsager. Kirkwood was like 59, but he didn't win the Nobel Prize, right? So, but it lists like everything he won on his gravestone. Yeah. And then Onsager, just as a joke, kind of just put like Nobel Prize. That's it, you know. So anyway, that's about Kirkwood. He won a lot of awards. But so he's kind of a famous guy for rheology, Kirkwood-Reisman theory for polymer rheology. But anyway, he did this thing too, this Kirkwood-Burr integral thing. So you calculate this thing, and from that you can get the free energy of mixing somehow here. The average value over all cells is da 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 da, and then somewhere he gets the free energy. That's a Kirkwood-Burr integral. I think that's just directly gives the free energy in mixing. It doesn't matter that much for our purposes because we're just kind of interested in the equations, I guess. But somehow, application, activity coefficients. Where does G come into this? It's a question. 1 gamma, blah, 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 blah. Well, somehow he gets the free energy from the Kirkwood-Burr. This is a different, that's the excess free energy, but it's not. Where does the Kirkwood-Burr connect to the? Oh, the question for ChatGPT. GI calculated by controlled volume. GI. Let's see, I don't remember how you get the free energy from that. Determine limiting values, GIJ infinity, blah, blah, blah. Results, application, must be right here. 6, as mentioned, blah, 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 blah. You know about that. You know about this. How is it? Oh, KBIs. The chemical potential derivative on the right-hand side can be calculated by KBIs through the relation below. KBIs is, oh, I see. So he's just got a relation. He doesn't explain where it came from. So you just accept that the chemical potential is given by these KBIs, by these Gs. That's the answer. Equation 11 relates the two. We don't know where that came from. I think you have to read Kirkwood-Burr paper or something to figure it out. He doesn't even cite it. Just says by this equation. I mean, you can imagine that there's some relationship between the organization of the material and the chemical potential of the component. So somehow they should be related, but how they actually are related, I guess somehow this equation does it, but Method, as we described in the methodology section. So yeah, we don't need to know how they did it. So anyway, somehow they get the chemical potentials. Once they get the chemical potentials, they can get the gammas. Once they get the gammas, then they can calculate the free energy of mixing, and then you can predict the excess Gibbs free energy of mixing, and from that you can get the phase behavior of it. In other words, you can calculate the chi parameter or the Hildebrandt parameter from that. Here he's got the chi parameter. So he's got, he shows experimental. If you look up the experimentals there, you can look at it. So they basically measured this on these, they're just organic molecules. They aren't polymers, right? So they can just measure this chi parameter using a cloud point, like what we did if that actually worked. But and then he has this two simulations. There's his simulation, Kirkwood Buff, and there's this Chen simulation where he does molecular dynamics. I think the Chen thing is there too. Let's see, hide floating controls. So the Chen thing, Chen's right here. So Chen does a molecular dynamics simulation. So this is a case for the Chen does a Monte Carlo simulation, right? So this, and he doesn't, I don't think he explains exactly how he does it. But basically, he's going to take the same system, right, and set up, and then do a motion and calculate the free energy of the system. Like, so he does kind of step motions, and his motions are going to include rotation of the molecule, like rotation of the atoms in the molecule, and the dimensional motion of the atoms around, like translational motions. And then I think that's it, like those two things. So he's going to have like a four parameters that he varies. So he's going to take his system, throw it in, like somehow get it to be random, and then vary those four parameters for every molecule in the system, then calculate the free energy by the approach of the molecules to each other and by the energy associated with about the things. Then sum the energy for the whole system and compare it with what he started with. And if the energy drops, he says that's good. If the energy goes up, he has kind of a random number that he calculates, and he says, like, log of that energy difference divided by KT gives me a probability. Is that probability bigger than or smaller than some probability that I picked for my cutoff? If it's smaller, he accepts the bad thing. If it's larger, he doesn't accept the bad thing. He throws it away, and then he goes back and removes everything. So basically, it's a sequence of moving and checking. And you let the system finally reach some kind of happy point where it isn't, you're not always just saying the free energy drops, because if you did that, the system would just collapse down to nothing. Like, it would just be a solid single state. That would be the optimum. So in order to get it at some temperature, because you're using change in free energy divided by test time. So log of the free energy change divided by KT is his test. So it depends on the temperature. So as you raise the temperature, it's more likely the system becomes random. As you lower the temperature, it becomes more ordered. So it's kind of like guaranteed UCST in that approach. Right. So anyway, that's what he does here. You can Google that too. Like, you can Google Monte Carlo simulation and work out kind of what it is. I think it asks you. That's why I'm mentioning this. It says, what page? Give you theory, book by whatever, and then explain what a binary correlation function is. So I kind of did that. How does this approach differ from Monte Carlo of Chen? So his approach, so the approach of our guy, he's doing molecular dynamics. So that's different. Like, he has potentials between everything. So if something moves, it's just a force balance between everything. So the velocity of things, so it's dynamics, so it's velocity and acceleration of particles, and the velocity is influenced by the potentials between the particles. So if the potential is high, the velocity slows down, or it can make it go the other direction. Right. So you just, in this case, it's literally like make the molecule and let it behave how it would behave due to thermal vibration motion. Right? So the things are randomly moving around, and they're subject to the potentials of each other. so they can repel and attract each other. And the impact of that on the velocity decides like the distribution of everything. Right, so it's different. There is no testing of the free energy in that system. You don't have to calculate the free energy. You can calculate the free energy. So you in that system, you calculate the free energy, but you just map it against time. So you say free energy starts out high and it's going to decrease and it's going to reach a number. And once it reaches some number, that's equilibrium. So that system, you're letting the thing just go on its own. There's no choice made in it. In the Monte Carlo, every step of the system, you make a choice. I mean, if it's free energy drops, you're happy, you accept. Free energy increases, you roll a dice. The dice are weighted by the temperature. And you accept or don't accept, depending on how the dice come out. So Monte Carlo is different than the molecular dynamics. Right? Molecular dynamics is no dice. Molecular dynamics, it just runs. You put in the rules, the thing runs. It's like a machine is just going to run and it's going to reach equilibrium at some point. The Monte Carlo is actually choices made for each step of the thing, each step that it makes. Right. So the Chen guys have this like Minnesota Monte Carlo routine where that was already written by someone else and they just plug their thing into it. And then so nobody here is inventing anything. That's what I'm trying to say. This guy literally bought a program to do this, I think. He says what he uses somewhere in the methods or something or other. But I think he's using, so several choices on how to do molecular dynamics. And he's chosen to use like a commercial, I think he uses a commercial software to do it. Somewhere in here, he talks about the software that he uses to do the molecular dynamics. System studied, MD simulations and isothermal large-scale atomic massive parallel simulator software. So this, if you look it up, that's just something you can buy. So that isn't usually the normal choice. Normally people would choose like lamps from Sandia, which is free. Right? And this thing you're going to pay like 50 grand or something to use it. So no one can really check no one's going to shell out the 50 grand unless they already have paid for it to check his thing. It can't be reproduced. That's one issue. The NPT, so isothermal, isobaric. So you can have different. So there's grand canonical is if you use the chemical potentials constant and the volumes constant and temperatures. So you have different parameters you hold constant when you do. You always have to hold something constant. Like you have fixed volume. So that would be like kind of doing Helmholtz free energy. Or if you let the volume float, then you can get Gibbs free energy. So he's letting the volume float in this case, NPT. You can also hold the chemical potential constant. That's called a grand canonical. So there's different things you can hold constant. Basically, you have to say what you hold constant when you do the molecular dynamics simulation. You have to hold one thing constant. So anyway, that's what that means. So, all right, that's that business. Let's see what else I can get through here. So the Chen and his simulations are different, but they end up with almost the same result, right? And he thinks his is better, but basically the Chi looks pretty similar, and the experimental is quite a bit different, as far as I can see. Even the curvature is different, right? So it's hard to tell. Like, I mean, since his is a commercial thing, you can't reproduce. But for his excess Gibbs, so he shows the things that are given are favorable to him, you know. So the excess Gibbs matches pretty good with experiment. The Chen thing with the Monte Carlo isn't. But then he also explains like kind of why the Chen thing deviates more. It's written in the text here why it deviates more. But so anyway, equation 2 is a Flory-Huggins equation, has a different from Hildebrandt. So he's using volume fraction and it divides by the molecular weight, right? So that it can account for polymer mixing when the things are glued together. And there's the chains of molecules are glued together, so that reduces the entropy. So you have to reduce it by that number, the n here. Then for systems, so if the systems are like 12, like this is meant for systems of 100,000, where n is 100, and he's got 12. And I think he actually, the way I remember it, he's doing 4, but it says 12 here. So if it's 4, like this isn't really, you don't really need to use the Flory-Huggins for this thing, especially if they're both the same. Like they're both the same, that cancels out. So it doesn't really matter in the end. So I think that for his case, where he has a small number, he probably didn't need to use Flory-Huggins. He could have just used Hildebrand equation. And then, so here it says like, well, when you calculate chi, so you notice, so this is important, I guess. We got a couple of minutes, but. So when you calculate chi, so it comes out a positive number, which you would say like positive chi, that means a positive delta G is going to equal chi, and the ln terms are small. And chi is positive. That means it's going to demix because the change in free energy of mixing is positive. That means it'll demix, won't mix. Right. So what's going on here? So that what's going on is that, so the chi is really small though, right? No, it's chi by V is 004. Right. So it's a small number. It's not 1. Right. So basically, that's a small enough number that ln of the thing divided by 12 is bigger, is larger than that enthalpy of mixing term. Right. So that even though you have a positive chi, it mixes. It means it could be close to phase separation, like if the temperature goes in the right range. You could get phase separation if you go to low enough temperature. Right? In other words, chi by T, chi has 1 over T in it. So if you go to low temperature, it amplifies that positive, then you get phase separation. So you can predict a phase separation point for it. But having a positive chi doesn't mean it demixes. Say chi is 0, then it would mix. Then chi can go slightly positive, and it can still be mixing, because this term can be larger, the negative term, the random mixing term. Right, so that's the point of this, is saying, why is it miscible? Because you'd expect with a positive chi, that means it's not miscible. Derive equation 9, show how equation 14 is the same as Gibbs-Duhem. So that equation 9, 6, 7, 8, 5, 6, 7, 8, 9. So this is just what we did. That's in the class notes. This equation is directly from the class notes. So we can just follow the derivation there. And then 14 is also the notes. The last 2 slides are on Gibbs-Duhem. So that's exactly the function. Derivative of the gamma, derivative of the gamma equals 0. So it's just using that there. So I guess that's an indication that that kind of thing is used like that. Then 3 parts of the following statement. All right, so for infinite dilution, the excess component's activity coefficient converges to unity. So that's normal, right? We expect the activity coefficient to match the composition. You expect the activity to match the composition at infinite, not at infinite dilution for the pure component. Like when X goes to 1, gamma goes to 1. This isn't exactly written right. Well, for all of the compositions, I guess this is quoted from him. Gamma gamma 2 have a value greater than unity, denoting positive deviation from the ideal solution. That means a positive chi. And behavior for the oligomeric blends studied an indication of unfavorable interactions. That's true. Chi is positive, it's unfavorable. So the same, the above mentioned will consequently result in a positive excess Gibbs energy. That all kind of makes sense. So just explain that. I mean, in other words, it kind of makes sense, except that the activity infinite dilution, anyway, that part, this first thing isn't right. I mean, it's not exactly, I mean, it should be when X1 goes to 1, that's not infinite dilution. I mean, it's infinite dilution for the other component. Anyway, this is just a restatement of what we did in class. So I guess I'm asking you to put that into your own words. Whatever I said in class and what he said here is the same thing. But how the gamma works against composition, you get the Henryan part and the Raoult part. So just kind of reframe that in your own words. If you have a problem, email me on it, we can try to help you get the right thing on this. Hopefully it's not too bad. And it's a paper that has a lot to do with the notes, like it's almost the same thing. So it's kind of useful paper to look at. But anyway, any questions or anything? This thing. All right, so yeah. Yeah, I did that, and I sent an email today or yesterday on that. Explain equation 22. So that's the thing about the orientation function. So you have this thing describes like an order parameter for orientation. So it goes from 0 for random and 1 for perfect orientation. Then it has a -1/2 if you're pointing in the wrong direction. And then the cosine has value of 1/3 for random, and it has a value of 0 for perfect, or 1 for perfect orientation, and then a value of 0 for opposite orientation. Average cosine squared. So that's how that works. That's just what it wants. What value does it have? What do they indicate about the chain orientation? Just like, I guess it's not really directionality in this one because the chains are just polyethylene, so there's no up and down to them. Just orientation. Yes. Anything else? Anything there? That's okay. All right. That was pretty weird when the book came up. I was like, that's a first.